Alright, hi there. So we're going to look at section 9-3, which again, this is a chapter for inferences from two samples. In this section, we'll look at two means, primarily from independent samples. Alright, so a key concept in this section is represent methods for using sample data from two independent samples to test hypotheses made about two population means or to construct confidence interval estimates of the difference between the two population means. And just other things here. So in part one, we discussed situations in which the standard deviations of the two populations are unknown and are not assumed to be equal. Now, this is the most realistic scenario of the ways you can look at two means. So this is what we'll focus on mainly, and then the stuff in part two will just kind of be optional extensions if you want to just kind of check that out on your own. So in part two, we'll discuss in two other situations, the two population standard deviations are both known, which again, that's usually not realistic, but it could happen in rare cases, so that's why the methods are presented. And then the other unlikely but possible way is the two population standard deviations are unknown, but are assumed to be equal. So between those two scenarios, the second one is a little more likely. And so again, we'll just focus mainly on the stuff in part one. Now just to define independent and dependent in this context, with analyzing two means, we say two samples are independent if the sample values selected from one population are not related to or somehow paired or matched with the sample values from the other population. And then we say two samples are dependent if the sample values are paired. Now, that could mean each pair of sample values consists of two measurements from the same subject, such as before or after data. That's probably the most common pairing. Or each pair of sample values consists of matched pairs, such as a husband-wife data, where the matching is based on some inherent relationship that's already existing. There are some examples of independent and dependent samples. So independent samples, researchers investigated the reliability of test assessment on a group consisted of, sorry, I should say one group consisted of 30 students who took proctored tests. Then a second group consisted of 32 students who took online tests without a proctor. And so the two samples would be independent because the subjects were not matched or paired in any way, like two totally separate classes. And an example of dependent sample could be students of the author collected data consisting of heights of husbands and the heights of their wives. So 5 of those are listed below. And then the data are dependent because each height of each husband is matched with the height of his wife in some way. There's some notation that we'll use for these methods in this section is just something like mu sub 1, just standing for population mean, sigma sub 1 for the population standard deviation, so still using Greek letters for population variables, n sub 1 for the first sample size, x bar sub 1 for the first sample mean, and s sub 1 for the first sample standard deviation. Then you can use those same symbols just with subscript 2 standing for those from the second population. Now, our requirements for the hypothesis test or confidence intervals of two means is that the way we'll do it most often is, again, the population standard deviations, both of them are unknown, and we are not assuming that the two will be equal. Now, second requirement, the two samples are independent. And third, both samples are simple random samples, so we see that come up an awful lot. And fourth requirement, either or both of these conditions are satisfied. The two sample sizes are both large, so at least over 30, or both samples come from a normal distribution, or roughly normal distribution. Now, this is the formula for a test statistic of a hypothesis between two means. So basically, you take the difference between the two sample means, subtracting the hypothesized difference between the population means, which will typically be 0, divided by that square root of, let's see, they're both of their sample variances divided by their respective sample sizes added up. And so just some more with that test statistic. So the degrees of freedom can be very complicated. But instead, what we're going to do in this book is we use the conservative estimate of degrees of freedom, which basically means you take the smaller of, say, the first sample size minus 1 or the second sample size minus 1. Whichever one of those differences is smaller, just use that for the degrees of freedom. Otherwise, the calculation can be quite long. And as for p-values, so we're going to use technology primarily, and then you can also get estimates from the t-table, but we can primarily use the t-table for getting critical values. Just a caution, before conducting a hypothesis test, consider the context of the data, the source of the data, the sampling method, and explore the data with graphs and descriptive statistics. Be sure to verify that the requirements are satisfied. Alright, then we'll go and do an example here. So researchers conducted trials to investigate the effects of color on creativity. So subjects with a red background were asked to think of creative uses for a brick. And then other subjects with a blue background were given the same task. So responses were given by a panel of judges. That's just kind of outlining that basically there were some judges that gave creativity scores, which you'll see on the next slides. And researchers make the claim that blue enhances performance on a creative task and test the claim using a 0.01 significance level. Just a quick requirement check. So the values of the two population standard deviations are unknown and assumed not equal. Good there. So the subjects were independent. Basically the red group and the blue group are saying they were independent people in those groups. And the samples are simple random samples. Both sample sizes will exceed 30, which you haven't really seen yet, but on the next slide shows that, yes, their sample sizes both exceeded 30. And so these were their mean creativity scores. So 3.39 for red, 3.97 for blue, just determined by the supposed panel of judges. And these were their standard deviations of their creativity scores. So just going through a hypothesis test and steps now. So the claim that blue enhances performance on a creative task can be restated as people with blue backgrounds have a higher mean creativity score than those in the group with the red background, group 1. So that can be expressed as mu sub 1 is less than mu sub 2. And then, so if that is false, then the opposite is mu sub 1 is greater than or equal to mu sub 2. So basically the red is greater than or equal to the blue. And it's actually writing those as hypotheses. So again, just always keeping some equality in the null hypothesis. And in the alternative hypothesis, just using that mu sub 1, so the red is less than the blue, mu sub 2. We're using a significance level of 0.05 for this one. And now because we have two independent samples, we are testing a claim about two population means. We're going to use the t distribution. That's the distribution we'll use for all these kinds of problems. Now for calculating the test statistic, so just kind of plugging everything into what we want there. So there's the red mean minus the blue mean, then minus their hypothesized difference of 0. Then here's the red standard deviation divided by that sample size, plus the blue standard deviation divided by its sample size, all square root. Once you evaluate that, you should be finding that the test statistic comes out to negative 2.979. And so now when we find either p-value or the critical value, we come to this step and show you how you can find the critical value using the t-table, which, by just a quick recap, in case you're not sure where to find the t-table on our Canvas page, I'm just going through a little navigation to find it here. And so the t-table is just right there. And also we're going to need the applets in a little bit, so I'll just go ahead and open that up now. Okay, then so for the t-table, we know that essentially in the area of I just realized there's a typo here. So we're using a 0.01 significance level. So this right here should be saying 0.01, not 0.05. Okay, so then when we come to the t-table, the area we want to look in is actually, so this area in one tail, because we're doing a left-tailed test, since it's a less than scenario. And so we're looking in this column here, and then for degrees of freedom, again, we're using the conservative one, which is just the smaller of the sample size minus 1 or the sample size minus 1. So of course this one's going to be smaller, so degrees of freedom of 34. So again, just looking at this column, go down to where I can find 34, trace it over, and I get 2.441. And since this one's going to be a left-tailed test, I just go ahead and make this critical value negative. That's where this critical value of negative 2.441 is coming from. And so that's one way we can say that since our test statistic is less than our critical value for a left-tailed test, then this will be a reject H0 scenario. And another way we can find it is with the p-value, which, by the way, some technology I would recommend is those two Statsmatic applets that are good for the types of problems we're going to do. And so they are, when you look at the applets, so under traditional inference, there'll be 2 sample t-test for means for the hypothesis test, and then 2 sample t-interval for means for when we do confidence intervals. 2 sample t-test for means, then 2 sample t-interval for means. Okay, and then so let's see, just to save some time, I plugged in the information into the t-test one already, right here, and then so it looks like once we start doing that is we've got all this typed in, so our mean, standard deviation, sample size for the red and blue groups. Click on begin analysis. Just make sure you're doing a 2 sample t-test in this drop down. You want to make sure that you've got yes selected for conservative degrees of freedom in this drop down. And then just make sure you have the correct alternative hypothesis here, which ours is going to be a less than, since in our hypotheses here, we have it as mu sub 1 is less than mu sub 2. So if you subtracted mu sub 2 over, it'd be mu sub 1 minus mu sub 2 is less than 0, which matches up with this one here. And perform inference. We get that same test statistic of negative 2.979, so we know we're okay. And our p-value is about 0.003, which is also close to our p-value of 0.0021 as stated here, which those would be close enough that we could say they reach the same conclusion. So just concluding this one, there is sufficient evidence to support the claim that the red background group has a lower mean creativity score than the blue background group. And then so we can also use a confidence interval to reach the same conclusion for this kind of problem. And this is just the formula set up for that, where we just take the difference of their sample means and add and subtract the margin of error. And so now the margin of error is just going to be, so the t critical value, just the positive one, times, notice it's the same square root of sample 1's variance divided by its sample size plus sample 2's variance divided by its sample size. And we're still using the conservative degrees of freedom, so for our particular problem, 34. Now if we're asked to go ahead and find a 98% confidence interval estimate for the difference mean creativity score between those with the red background and blue background, and we just be plugging everything in here, and since we're using a 0.98% confidence interval, that means on the t-table that the area in 2 tails is 0.02. And so it actually means when I look at the same 34, I'm using the same critical value for this problem. And just plug in all of that in and get that the differences would be between negative 1.06 and negative 0.10, roughly. And by just you can do that also with technology. So again, we can use the 2 sample t interval for means. It'll just look like this, and it's good to change it to the mean standard deviation option. Just save time, plug that in over here. So I've got all that typed in, I can just click begin analysis. Make sure everything else here matches up. I've got the 98% confidence interval I want, conservative degrees of freedom, yes. For inference, it gives me those same interval limits there. All right, and that's that. So we'll reach the same conclusion and leave the rest for an extension video.